regular structure naturally suited to domain decomposition and very efficient parallel computation. So that it has that feature, and it also, finite element method provided great flexibility to treat compressible flow, spatially varying material properties, real equations of state, and lithospheric plates at the surface. Okay, this is the grid. Shows how I able to construct the grid. Started by projecting the regular icosahedron onto the spherical surface to divide the spherical surface into 20 equal spherical triangles, and then subdivided that grid by connecting the midpoints of the edges with great circle arcs. And just repeating the process, I could get as fine a grid as I might desire. And I'll show a little later, uses a grid another factor of 2 finer than this one, and in 3D. This 2D grid was then replicated in the radial direction to get the full 3D grid.
Dr. Baumgardner, can I ask a question?
Yeah.
When you say that you did that, is that, for this, you don't have a graphical user interface that you're just specifying the number of nodes, right? Is this all code that you're writing, and then you're creating a visualization of what it looks like to confirm that you have what you need? Or how did you actually start from your coarse mesh and progress to the fine mesh?
Well, generally in this field, it's essential to have visualization. You have to be able to visualize what you're doing. So very early on, I wrote the graphics routines to visualize these. So I wrote the graphics to create that image there.
Okay.
And that was involved the ability to slice the grid and open it up where you could see an interior surface like that.
So you had to write the code that determined the spherical dimensions and how it was going to be partitioned into its elements, and then it would loop with the visualization so you could see what you've done and can iterate that way?
Yeah.
Okay.
So in those days, I was doing this at Los Alamos. There were graphics libraries available, and so I utilized the graphics libraries, but the graphics I wrote were in terms of these, what we call graphics primitives, originally written for pen plotters, way back in, more than, like 50 years ago. There were commands to, lift the pen, move to a certain point, have the pen down, then draw a line to another point, and other commands to fill in polygons. And so the graphics I have, I still use these graphics. I wrote myself back 40 years ago.
Okay. So, and that's sort of the general procedure if you aren't using a commercially robust program like Abacus, right? You kind of have to start there.
Yeah, these,
Okay.
Since then there've been explosion of graphics tools with good user interfaces, graphical user interfaces. So, in my case, I find that, again, you've got so many millions of numbers. There's no way you could look at on the screen at the numbers, or you've got to represent the data visually to make sense of it, to understand it.
Right.
And so, so I like, when I'm running a calculation, I commonly have graphics running at the same time, producing visual images of what I'm calculating, so that, if I so desire, I can log on, access those graphics files, display them, and see what's going, how the computation is going.
Okay.
Yeah. So, there's, as you might expect, hard work there.
Sure.
Anyway, today it's a lot of these tools you don't have to reinvent. They're already there. They're not nice. It's mainly a matter of learning learning the features of the user interface. Learning how to do that, and hopefully during this class y'all will be starting to do that.
Okay. Sure. That answered my question. Thanks.
I have one. In this mesh of your object of the Earth here, is it two linear scaling proportions of the Earth, or is that irrelevant within the finite element code?
Can you ask it? I'm not understanding your question.
Basically, did you have to put in some kind of corresponding length scale per node that would relate the object that you meshed to the proportions of the Earth?
Generally speaking, I used the actual dimensions. I wrote this. Units were SI units, meters, but the cells were kilometers across.
Yeah. Okay.
And so I tended to use the actual numbers that that physics required. That's you can scale these problems, but you can shoot yourself in the foot if you're not careful. I find it just more straightforward, at least for the problems I did, to use the actual numbers.
I was just curious because on something on the magnitude of the size of the Earth, when you try to, capture the physics within a single element, how small do you have to go? Like within a single element, that might be kilometers in dimensions. Are you actually capturing the physics of the convective movements, or would you have to go even smaller?
Well, there are places where that's a big issue, that you really can't capture the small scale flow. So one thing that I did and other people in the field did, you can scale some of the physical quantities so that maybe in your term, so that the Rayleigh number was smaller. In this case, in my case, it's so that the Rayleigh number was smaller, so that the length scales were longer, and so that you had to, often I did that so that I would not be under resolved, so that I had enough spatial resolution with my grid to do the calculation accurately. So we'll get into that kind of issue. That's a big issue of making sure that you're getting accurate answers. One common practice is that you